Welcome to a lesson with Dr. Powell. Let's take a look at how we can represent a matrix as a scalar and even take this scalar written as x here and put it into vector entries. Because normally if we have a vector in R3, maybe we have something like 2, 5, 4. All of these entries are in R. But now we have our entries looking like this. They're polynomials. How does that work? Can we still decipher what that might mean? Okay, so we're treating our matrix right here as a scalar. Now, how does that work? Well, scalars give you a certain action on a vector. Like suppose you have the scalar 2 and you want to act on a vector like 1, 5, -2. What happens? Well, it acts on this vector by just multiplying each component, like 2, 10, -4. So it acted on this vector. You could describe this action actually as a matrix if we wanted to. We could describe it by this matrix, and then the vector action, we just put the vector as a column right over here, and we matrix multiply, and we'll notice we get the same thing. So really, when we have scalars, scalars really represent or can be thought of as representing action by a matrix itself. So that leads us to the question, can we just let any matrix at all represent a scalar action? This idea is helpful when we start looking at how to think about raising matrices to high powers, or even changing the basis of the matrix, like multiplying to the right and the left by matrices to turn the matrix into a simpler form. And there's lots of applications for that, maybe where it's diagonal or something like that. This idea kind of feeds into that. So right now we're going to focus on this idea. What does this vector look like? How does x act like a scalar? Well, we know already that if we plug anything in to x, its action on a vector like 1, 5, -2, we would just do a matrix multiplication. And we just do a matrix multiplication of this, and so we would end up getting +2, and then let's see, +2, so 3, so -2 if I'm not mistaken. Okay, let's see, yeah, okay, and then we have 1 and 4, so that would be 5. Okay, like that. Okay, so we know how it acts. Now, back to the question. What do we do here? Okay. So our action of scalars on vectors as well, and we're letting x be included in this, is such that, like, if we add two things right here, then this scalar action actually distributes, or you can take this vector distributing to both parts. And likewise, when there's things inside, inside right here, like if there's an addition in here in the vectors, like this is added with something else, like if you have two vectors with a scalar, like say u plus v, and we have a scalar acting on it, that distributes as well. So using that idea here, we can think as follows. We could first split this up into parts, such as we could do like say x squared x 2x squared. And we could say that's added to 1 -2 2. So we can split it up that way. Further, we could okay, further we could think of this as being something like as follows. We can think of it as being like x squared, let's see, x squared comma 0 comma 2x squared plus 0x0 plus 1 negative 2 2. You see at least why this works. I mean, these two guys right here add up to this. Now, why would I split it up like that? Well, what I'd like to do, see how I separated out the x squared portions and the x portion, because here I can actually take this, I can factor an x out of this because I have zeros there. And so really this vector is the same as x times 0, 1, 0. And this vector over here is the same thing as x squared times 1, 0, 2. And then that guy is just like itself. So I just kind of factor the x squared out of these vectors and the x out. Now, why is this nice? Because we actually know what the action is now, because we know how x acts on this guy, and we can figure out how x squared acts on that guy. Okay, what is x squared? It's just this matrix squared, the square of that matrix, and then you act on that vector like a column. So x, you act on this vector as a column, and then you just add that one up. And then we should get what this vector right here represents. So now what is this? X times this is a column. Now this actually picks out the middle column right here. Matrix multiplication would do that here. So let's kind of write out what we have. So we'll write all the vectors as columns now for just a minute. So x times this would just pick out that column. So 0 minus 1, 0. And then x squared times this. Okay. All right, so we have x squared times this thing. Well, first, maybe let's just do x times that vector. All right. So 1, 0, 2. 1, 0, 2 is the same thing as saying like 1 times that column plus 2 times that column. Okay. So in our minds, we can kind of think negative 2, negative 2, negative 4, because 2 times that, and then just add across. So you get negative 2, negative 1, and negative 3. So that's negative 2, negative 1, negative 3. Okay. So we have, so far we have negative 2, negative 1, negative 3, but realize we still have x multiplied onto that. All right. Then we'd have to plug that into, then we take that and we have to plug into x again. So then we have negative 2, negative 1, negative 3, and we plug that in. So here, maybe we'll just do it this way. We'll just take the row and the column, just dot products here. So the first entry would be so let's erase this right here. So the first entry of that, would be a positive 3. And then you take, negative, so let's see, positive 4, and the negative 2 would just be a positive 2. And then right here, that'd be negative 2 plus 6, which would be 4. Okay, so this one right here corresponds to x squared times that. We just took the matrix squared and multiplied to that vector, the matrix times this column vector, and then adding that vector. So we just have these. We add across, and we will come up with the result that we desire. So let's erase this right here and put down what we have. All right. So this is equal to, we have 4, negative 1, and 6. So we have just successfully written this vector with x and with entries with x's in it, polynomial entries, but under the condition that we know that x is actioned by this matrix. So if x is actioned by this matrix, then this vector will live in R3. If x is unknown what kind of action it is, then this vector does not live in R3. It doesn't even live in a vector space. In fact, it would live in something like polynomials cubed, or to the third, which actually is a Cartesian product, meaning tuples of polynomials. So it would live in here. However, if we make the statement that X is this action, then it actually will live in R3. The idea, it's like it's actually um, a quotient module, if you will, kind of like a quotient vector space, but a quotient module in that here, and the result is the vector space R3. This thing will live in there, and this is what it looks like. Thanks for watching.